Good morning, sir.
Morning, sir.
Hi. Sir, good morning, sir.
Sir.
Good afternoon. Shall we start, sir?
Yeah, we can start, sir. Okay.
Yes, sir. Yes. So, participants, good afternoon to everyone present here today. So, it is one of the wonderful and remarkable day today. We are gathered here to attend the workshop on robotics on behalf of Ramco Institute of Technology, Rajapalayam, under Institution of Engineers India Student Chapter Mechanical with pantechelearning. So we Ramco Institute of Technology is from the Ramco Cement Group, which is located near Rajapalayam. We have 5 departments. One is mechanical. So from this mechanical department, we are organizing this webinar today. It is one of the wonderful opportunity we got to work along with pantechelearning. So I first and foremost thank pantechelearning for giving me this opportunity. I also thank our principal, DGM, vice principal, and the faculty coordinators and whoever behind this webinar, our workshop to conduct this, helping me to conduct this in a fruitful manner. So hope this workshop is a need of our, as robotics is one of the most essential thing. Most of the industries are accommodating robotics nowadays to automate everything. So this is one of the need of this century. So I hope participants, you all will be very much enjoying the session. And I request all of you people to be in contact with the resource person and get as much as information so that we can develop a better future. So with this, I close my words and I hand over the session to our expert speaker of today. Thank you.
Okay, good afternoon, everyone. So I'll be taking the session today. I'm Nivin. I'm from pantechelearning. So I work in embedded engineering. So I also, that is part of robotics is also part of my field of expertise. So I'll be just taking the class today, generally about robotics. So I'll share a PPT, and we'll first start with the PPT, and we'll go with the flow, like from the history and throughout the currently right now what is happening, and then we'll go into some technical practical things. Okay. So if you have any doubts or anything, you can post it in the comment section. So So we will just start with the basics of robotics, like history of robotics and all that. And so before that, initially, just a brief definition of what is robotics. We all know about robotics, what is robotics, and everybody has a basic idea of what is robotics. So still, we'll just start with the basic definition of what is a robot. So it is a general term, so we cannot just pin down this is robot or this is particular thing, but still we can use this definition. So robot is a machine. Machine can be in general anything. So especially one that is programmable by a computer. So this is not just not the case in so many robots. A robot can be purely mechanical with some programmable hardware or without some programmable hardware. So we'll see all type of robots throughout the session. So especially a robot is a machine, especially one programmable by a computer, capable of carrying out a complex series of actions automatically. So that is the one important thing here, automatically. So a robotic system means it's a fully automated system. So we just need to initialize the system with some instructions. So these instructions can be any kind of coding. So it can be high-level programming language, or it can be simple codes, or it can be binary, or it can be mechanical setting up. So this initialization can be anything. But after that, the machine should work automatically on its own without any external guidance. Then robots can be guided. So there is also it can be okay. So like I said, it can work automatically, it can function automatically, but still you through the functioning we can also give commands. So in some so this type of robots are guided robots. So the robots can be guided by external control devices, or control may be embedded within. So control may be embedded. Fully autonomous means there is no need to give any guidance. It can automatically work on its own based on different kind of inputs it can take from the external environment. Then robots may be constructed to take human form, but most robots are machine designed to perform a task with no regard how they look. So robot means basically like mostly in general when people think about robots, they think about a humanoid robot, a robot which has a human form with a human skeleton. But most of the robots, most percentage of the robot is does not have any doesn't look anything like humans. So it is just a functionality, whatever task it is performing. So it is purely designed based on that functionality. So how it can easily finish that task. So this designing of the robot is basically based on that functionality. And there are also humanoid robots. Humanoid robots have applications, but there are not that many wide applications for humanoid robots. It is not that much favorable to make a robot look like humans because there is no functional, implication for that type of things. But but robots can be of any shape or any. And then a brief history of robotics. So robotics robotics means, like I told you, robotics these days, if you start talking about robotics, mostly everyone thinks about some kind of humanoid robot that we have seen in movies or uh, other places. So here, robot can be anything. So robots have been existing since the ancient civilizations, like the Greek and the Egyptian civilization. So so these days robots are electric powered, but in the old days, before the emergence of electricity and all that, it used to be water power for different kind of ceremonies and things like that. So then in 14th and 19th century, with the arrival of different type of European kingdoms and all that, they have tried different type of clockwork driven robots for entertainments. So we can using cogs and things, we can make gas powered, air powered robots that does not need any fuel or fuel or electricity by just rewinding. Just if you take a clock, the pendulum clock, you can see we can just wind the clock, and it will just work on its own for the whole day without any other external input, power input. So it's the same kind of robot that used to be the Europeans used to make in 14th to 19th century, and then in 19th century with the arrival of late 19th century with the arrival of electricity and the mechanical, the heat engine and all that, the new type of robots came into existence. So in the first type of first motor-driven automata robot was built in 1928, and then in 1961, first fully finished industrial robot was built, and it was called Unimate, and then in 1967, autonomous mobile search robot. So I'll just explain, and this robot is called Shaky, and then Stanford arm in 1969, dexterous electric motor-driven robot arm. So these are all, I'll explain all this in detail. So these are all different steps in robotics, different developments that happened in the 20th century, different developments in robotics. So this is all based on, purely based on industrial purposes. And then Unimate, about Unimate. Unimate was developed by George Devol, and Unimate was the first industrial robot which worked on General Motors assembly line at the Inland Fisher Gate plant in Ewing Township, New Jersey in 1961. So this was made in US in New Jersey for a plant for a General Motors plant. So we know General Motors. We have so many vehicles, Chevrolet. All these cars are made by General Motors. So GM has been in existence, since the early 20th century, and they have human-powered plants. But this is one of the first robot-powered industrial plants for GM by General Motors, and this robot is called Unimate, and it can perform one single task. It is for picking things and then putting things in different places. So this was used for casting and all those things, because it cannot be handled by humans. It's very dangerous for humans because it's very high temperature, so humans cannot do that. So humans used to do it, but it is still very dangerous. So this robot was introduced for that single purpose, picking up things and putting it in different places. And the second one is Shaky. So like the name, Shaky means it can be programmed. It is a general purpose mobile robot. So if you take Unimate, it can perform only one task. It can pick things and then put it in different places. So it can do one thing. Here so we can give a single instruction. So each time you have to give instruction. If you want to move it left or right or up or down, each time you have to give instruction. So there should be a human present there giving commands all the time. But in Shaky, it is a general purpose mobile robot that is able to reason its own actions, while other robots would have to be instructed each individual steps by completing a larger task. So Shaky could analyze commands and break them down into basic chunks by itself. So it is same as like making a programming application. We don't need to give each instruction. We can build an algorithm based on that algorithm. Based on a flowchart, we can create our own program. And this program means it is a number of commands. It is a number of commands and some number of arithmetic or other kind of logical operations. So these commands, you don't need to execute these commands individually. You can just give it you can run it as a whole, and as we schedule, it will just work on its own without any kind of guidance. So here also the same way, Shaky is a general purpose mobile robot. So it can move around, and it can, based on the one single program, it can perform a large task by just dividing the the program into a smaller and smaller steps. So it can be used for different kind of things. That's why it's called different type of things. That's why it's called a general purpose mobile robot. And then Stanford Arm. Stanford Arm is an industrial robot. In industrial robot with the 6 degrees of freedom, designed at Stanford University by Victor Schreiman in 1969. It was designed in 1969, and it has 6 degrees of freedom. It means it can move in 6 different directions, 6 degrees of freedom. So it can be used in wide range of processes. For like, it was research. This was a research and development project. This was a research project, but still it can be used in so many different applications. So this is very much advanced compared to Unimate. Unimate has very limited degree of freedom, and it can move only in certain directions. So it can be designed to move in different directions. And developments today. So this is history of robotics in general. Different. So we've seen from like beginning from the ancient times to the recent in 20th century up to 1969 what happened. So now I'm not going to. If you take robotics today, you can take robotics today. You can we can talk about a lot of things, because these days, if you take any kind of technology, it doesn't mean one thing. We can integrate so many things into one system. So if you take embedded system, for example, I'm working in embedded system. If you take, it used to be in embedded system used to be just microcontrollers and programming microcontrollers. But these days, if you take embedded system, we can do many things. We can integrate machine learning, deep learning, different type of data science, blockchain. We can integrate computer vision. So robotics, different type of computer vision robotics into embedded system. So embedded system can mean any of these things, and it doesn't mean microcontroller. We can also use single board computers these days, very high level computers provided. Like if you take computers like NVIDIA computers, these are very high end computers. They can be used for very high level programming processing. So if you take robotics, just the same way. If you take robotics, if you discuss robotics these days, we have to cover a wide range of areas like AI, artificial intelligence, data science, and computer vision. But I'm not going to go into all that. We'll just and also autonomous navigation and all that. I'm not going to all that. I will not be going into all that. We'll just go with the basic robotics, what is happening in basic robotic development these days. So also automation will also come in that, like basic robotics. So if you take robotics these days, this is one of the most popular names in robotics, ROS. So ROS means robotic operating system. So robotic operating system is widely used in development and industrial cases. So it's still in its infancy. It's only been implemented in the in the second decade of the 21st century. So it's only been there for like less than a decade. So it's still in its infancy, still it's in development. New packages are still developed. So, but still we can use it for so many different developmental, and also we can also make products using robotic operating system. So I'm not going to go into details of robotic system, how to like make a robotic system application, but we'll just talk about robotics operating system and what is it, and then how we can implement a robotic system in different cases. So robotic operating system, this is a definition of robotic operating system. So this is a Wikipedia definition of robotic operating system. Robotic operating system means ROS, or ROS. It's an open source robotics middleware suite. So it's not exactly an operating system like a conventional operating system, like a Linux operating system or any kind of Unix operating system or Windows or Mac or iOS. It's not a conventional operating system. Although ROS is not an operating system, but a collection of software frameworks for robot software development. So it is a collection of robotic operating, collection of software frameworks for development of different kind of robotic frameworks. And it provides services designed for a heterogeneous computer cluster, such as hardware abstraction, low-level device control, implementation of commonly used functionalities, message passing between processors and packages. I'll explain all these things in detail: hardware abstraction, low-level device control, and all that. So here it provides services designed for a heterogeneous computer cluster. So heterogeneous means like if you take internet is a heterogeneous collection of hardware. It is we can connect any different kind of hardware to internet that has a internet network connectivity, and we can communicate. And like using this device, we can communicate. Like for example, you can take a mobile device, a smartphone, any kind of smartphone, Android or iOS or any kind of smartphone. Or if you can take a systems, different kind of PCs, laptops, or any other kind of PCs, or any device. So many devices, and also in IoT means we can connect all this small hardware to internet. So internet means a heterogeneous collection of hardware. Same as in ROS, we can connect different kind of heterogeneous computer cluster. So these computers can be running in running. They could be running different OSs, operating systems. They could be implemented based on different hardware architecture. But still we can integrate all these hardware, and we can make a integrated system, a robotic system based on if we use robotic operating system. So robotic operating system basically means integrating different components to make a complete system. For example, in modern day, robots doesn't just mean the actual robot. It means there is a software support, and there is also some packages running, and it cannot be all implemented in a single robot. So there will be a collection of systems working for the same robot. There will be a computer, there will be multiple computers or servers or supercomputers, working, doing different kind of data processing for the functioning of the robot. So if you take for example, if you take a Mars rover or some kind of a space rover, it is not the robot. The whole system that is running in robot is not implemented in the rover itself. The rover collects the data and it sends the data to the Earth, and on there will be systems, supercomputers. They can run this process this data for different kind of applications. So similar to that, not that high level, but similar to that. Here also we can use multiple systems, multiple computers to do, make a robotic operating system. So I'll give you examples of that. Then we'll see what is ROS in details. So it is hardware abstraction and low level device control, and it was created by California-based Willow Garage, now maintained by Open Source Robotic Foundation (OSRF). And then ROS means plumbing, tools, capabilities, and ecosystems. I'll explain all this: what is plumbing, what is tools, and all that. Before that, what is hardware abstraction? So hardware abstractions are a set of routines in software that provides programs with access to hardware resources through programming. So set of routines in software that provides programs with the access to hardware. So the programs which has hardware access to hardware, different kind of hardware resources. And so hardware abstraction means using these different kind of softwares, interfacing interfacing a software, a high level software to a hardware using some kind of intermediary software. So there can be a high level GUI like a human, which can be controlled by a human, or we can analyzed or monitored by a human, and then then that high level commands or whatever data is converted to a low level data in a low level software which has direct access to a hardware. So that is hardware abstraction. That's what hardware abstraction means. So programming interface allows all devices, in particular class C hardware devices, to be accessed through identical interfaces, even though C may contain different subclasses of devices that each provides different hardware interface. So C devices means normal computer devices, any kind of computer devices. So in that computer devices also there is high level, low level, different kind of depending on the processing speed and the network connection capabilities and all that, they can be classified into different kind of hardware. So this so programming interface allows all these devices to be accessed through identical interfaces. So identical interfaces means in ROS we can use mainly in ROS common wireless fidelity networks, Wi-Fi networks are used, or we can use LAN networks, local area networks, or we can use Bluetooth or different kind of wireless networks to make a communication interface between all these hardware. So there should be some kind of common, identical, common connectivity, Bluetooth or Wi-Fi or some any kind of networking, other kind of network. So there should be a common interface, network interface between these hardwares to communicate. So the meaning of the reason for the communication is, like I told you, so different hardware will be running different kind of processes. For example, if you take a SLAM robot, SLAM means a autonomous navigation robot.
Good answer.
Autonomous navigation robot. So in a SLAM robot, first of all, we need a hardware, a hardware controller which can control the motors, different actuators. So it could be any kind of motor, DC motor, or a stepper motor, or it could be servo motors, or any kind of motors, or any other kind of actuators. So we need basic controllers to control these actuators, and then there will be some kind of so SLAM means there should be some kind of mapping mechanism. We can use different kind of mechanisms in mapping, like we can use LiDAR. LiDAR means with mapping through light. So light means we can use either IR or laser to map. So radar is mapping, uses RF frequency, radio frequency signals for mapping, and sonar uses normal sound wave, audible sound wave to map. So LiDAR also same works based on the same principle, but LiDAR is mostly used for indoor mapping. So mapping an indoor area. It's not used for a very high range applications. It's used for low range applications like up to 20 or 30 meter range. So radar means it can range up to kilometers, kilometer distances. But LiDAR means it can only range up to, you can only detect things up to a particular range like 30 meters. So it is mostly used in indoor applications, indoor mapping. So this device is used for mapping an area. And then if you take another type of mapping device, we can use 3D cameras, different kind of depth cameras. So these depth cameras can be used for making a 3D map, three-dimensional map of the environment. And then this data should be collected by another hardware. So this hardware can be some kind of single board computer, like a Jetson Nano, or it can be a Raspberry Pi. And then this should be passed through, this data should be passed through a high processing system, like a normal PC with a 4 GB RAM or 8 GB RAM and a GPU. So the GPU and RAM means it can process this data very fast. So we can use some kind of a tool like MATLAB to process this data. So in this case, in this SLAM case, we have three hardware here, like a very low level microcontroller, which can use very low level microcontroller, which can be used for controlling different type of actuators. And then there is a high level single board computer, which can collect data from the sensing device. And then there is a third device, that is a PC, which can process this data and create a map, and then create a path from A to B. So if we can just declare, we can just give command, go from A to B. So this is how. So in this case, there is this is an example of another type of hardware abstraction, because in this case, MATLAB, if you are using MATLAB, MATLAB directly don't have any access to any hardware. So there will be some other software ROS packages which can access this hardware and which can provide data for MATLAB. So that is hardware abstraction. Then what is ROS? Then we saw the different components of ROS, plumbing, tools, capabilities, and ecosystem. So plumbing means ROS provides publish and subscribe messaging infrastructure. So like I told you, it's integrating different type of hardware to make a single single system, make a single synchronized system which can work based on some kind of idea. So here, to do that, we need to send messages from one system to another system, and also vice versa. So here we can use publish and subscribe type of messaging to do this operation. So publish and subscribe is used in many other cases. If you take internet protocols like MQTT, it also uses publish and subscribe method to send and receive data. So here also it is publish and subscribe. So publish and subscribe means just the same as the word says. Publishing means like if you have a journal, some kind of magazine or something. If you publish, if you subscribe to that magazine, you'll get that magazine weekly or monthly or daily or whatever it is. You'll get it on a periodic basis. You'll get the data. If you get the magazine, if you subscribe to this magazine. So same as that, here also, if you subscribe to a particular topic, so instead of magazine or anything, we can call it a topic. A topic, then you will receive data, any data published based on that topic. So publishing means there is a topic, common topic, and you just publish the topic, and then any device that is listening to this common topic can receive receive this data. So this is just to avoid any kind of confusion. You don't need to pair devices. For example, if you take a communication protocol like like Bluetooth. In Bluetooth, we have to pair two devices to start the communication. Initially, we have to pair the devices, whether it is two mobile phones or a headset or a laptop or a headset, whatever it is, you have to first pair these devices, or even if it is a basic Bluetooth module that can be interfaced with the microcontroller. We need to initially pair the device to send and receive the data. So that is one problem there. We have to initially set up the whole communication. But in publish and subscribe case, there is no pairing. The device should be connected to a common network. It can be a Wi-Fi network or a LAN network, and then we can send the data based on with the topic. So any device that is listening with the program of with that topic can receive that data. So there is no need to. So if you need to add a new device, you don't need to pair the device to the pair or connect the device. You just need to connect it. Simply just connect to the device to the common network, and then you can run the same program with the subscription topic and subscription topic. So you can add that device to the same cluster. So it is a clustering of different. So that is the advantage of using publish and subscribe type of messaging. And then tools, different kind of tools. So ROS provides an extensive set of tools for configuring, starting, introspecting, debugging, visualizing, logging, testing, and stopping distributed for computer systems. And so tools mean they'll develop each and every tools periodically, like twice a year or once a year. They make new tools or make new packages, new systems. So based on the new developments in the hardware, new hardware. Whenever there is new hardware, high-end capable hardware, then they'll develop their software systems into more more capable of utilizing this hardware capability. Then configuring. All these tools can be used for configuring, starting. So initially, configuring means initial configurations, like how to connect a device to a network for this clustering, and then starting how to initialize the devices. Then introspecting, different kind of like checking for different type of devices and all of that. Introspecting means like internally, whatever there is some problems or whatever devices are connected and all of that. And then debugging, different kind of error corrections, and visualizing. So in mapping case, we can use the visualizing part. We can visualize the map by using the sensor data. And then logging means logging the data to make a memory. So we can use this for future purposes. For example, if you make the map of a area of an indoor place like an office or a house or something, then you can use that map for making autonomous robot of any kind. Then testing, different kind of testing, and stopping distributed computing systems. Then capabilities. So ROS provides a broad collection of libraries. So there are like so many different libraries and implementations are there useful for robotic functionalities with the focus on mobility, manipulation, and perception. So perception means so mobility. First of all, mobility means we can like autonomous navigation and all that. That is called mobility. Mobility means we can a robot that can travel from that can navigate from one place to another without any human help, by just avoiding automatically, by avoiding any obstacles and then finding its own path. So just not simply by using some kind of obstacle detection sensor, but also finding its own path, finding doors and doorways and hallways, and then navigating to a particular room. So it may have to take turns and all that. So so we don't need to give any commands. So this so there are so many different kind of SLAM libraries and packages are available in ROS. Then manipulation means for we need to manipulate the robotic system for different applications. So like controlling the system, even if you are trying to build an autonomous robot, still it should be manipulated to set up the whole thing. So we can use this type of manipulation software. And then perception means different kind of sensors, and using the sensors like the lidar or 3D depth camera. So we can use these sensors to get the data. Then ecosystems. So ecosystem means ROS is supported and improved by a large community with a strong focus on integrating and documentation. So here, so we can you can go online and you can study ROS on your own. We don't need to you don't need to have a mentor, but if some because it's open source, so many ROS itself has an official supporting website which has all the documentations about all different packages and how to set up the packages and all that. So you can go online and you can study it on your own. And then key features. So we already saw the hardware abstraction and low-level device controlling and all that. Programming language independent. So we can use so many different programming languages in ROS. So like C, Python, C++, Python, MATLAB programming. We can use any kind of, so it's just programming language independent, and implementation of a wide range of commonly used tools and algorithms. Commonly used tools and algorithms. So for example, if you take in case of pathfinding, so not just in robotics or autonomous navigation, pathfinding algorithms like digital algorithm, it is used in so many cases like networking, it is used in so many different places. So digital is for finding the shortest path. So we can implement digital algorithm using ROS packages, and also any kind of other SLAM algorithms can be implemented using ROS. So there are like these algorithms may already exist, but you can there is equivalent packages for all these implementations for all these algorithms in ROS. Message passing between processes, OS independent. So it is OS independent. So for example, in the example that I just explained, the SLAM robot where there is a Raspberry Pi or a or a Jetson Nano and there is a Windows system or a Linux system, and there is a microcontroller. So this microcontroller could be a very basic microcontroller, like any kind of microcontroller. That could be an Arduino microcontroller, could be a PIC or ARM microcontroller based on some Harvard or whatever architecture. So it could be based on ARM architecture or some other architecture. Most of the some of the hardware microcontrollers are based on ARM architecture, and then there is also the single board computer like Raspberry Pi or NVIDIA, Jetson devices. So these devices are implemented based on ARM architecture. So their core is based on ARM ARM architecture design, but still they can communicate with the 86 architecture device, like our normal Windows systems or Linux systems. So the normal CPCs, the Intel processors are built based on 86 architecture. So still this device running running on 86 hardware, running a Windows system, can communicate with the Linux system, a Unix system, which is installed in a Raspberry Pi, which is based on a ARM architecture hardware. Still we can communicate. So this means message passing between processors, OS independent and also hardware independent. And then standardized package management, different kind of. So these packages are standardized. Standardized means there are like certain rules which we have to follow. So they are for like interface easy. So compatibility. So any kind of standard is for compatibility. So here also the packages are all standardized. They all follow certain rules, so they can be compatible with the different hardwares. So useful set of shell commands and utility with the tab completion. So there are some useful set of shell commands which you can use in testing cases. And tab completion means you can use the previous commands that you used by just using tab. Then ROS concepts and components, ROS client libraries. So there are so many different client libraries are there, and these client libraries are implemented in Python, C++, Lisp, MATLAB, and then experimental client libraries and implemented in Java with Android support, and also in Lua programming. And then operating systems. So we can implement ROS in operating systems, supported operating systems. So mostly for single board computers, Ubuntu OSs are used. Ubuntu like Unix OSs are used for these. And then in experimental case, we can use Debian, any kind of Arch or Debian OS or Fedora or Gentoo or Mac OS, operating open source, or Windows OS. Then supported robots. So these are the different type of robots that has been implemented using ROS operating system. So then different kind of sensors which can be used in robotic operating systems. So we have already discussed about the LiDAR and the depth camera, 3D camera. So here, so these are different type of LiDAR devices. This one is a one single dimensional. So the time of flight LiDAR. So it can just send a single signal and receive the signal. And then here there is a this one is a two-dimensional mapping device, LiDAR device, and this one is a three-dimensional mapping device. And then these are two depth cameras. So first one is an Xbox, which we can use for in kind of different kind of gaming applications and virtual reality applications. Then so 2D rangefinders. So these are like laser scanners, SIG lasers, Microsoft Kinect, and Asus Extreme. These are the different devices we can use in different sensors, input sensors, which can be used for mapping. And then sensors. So if you take other type of sensors like cameras, so then monocular camera and stereo camera, then USB, normal USB, UVC, and rewired camera, then video streaming, GStreamer, different kind of cameras that can be used and different kind of hardware devices that can be sensors, and different hardware devices that can be used. Force, torque sensors, and motion capture systems. Then pose estimation system, IMU systems, IMU or GPS systems. So if you take IMU, it consists of gyroscopes or magnetometers and accelerometers. These are all used for pose estimation. Then GPS means locating one place, locating something in one place. Then audio and speech recognition. Then RFID. So RFID means we can use RFID for autonomous navigation purpose. The localization, we can use RFID for localization. So RFID means radio frequency identification. So there is a reader. In RFID there are two components. There is a reader and there is a tag. So this reader can read any identical tags. So all these tags have their own unique identity, So this identity is based. Identity means they have a unique number embedded in the card. So once you once you swipe or tap the card on the RFID ID reader, the reader will read the number. So based on that number, the reader can identify this is the particular card. So we can fix this card in different places. If you take an indoor area or an outdoor area, you can fix these cards in different places. So then we can fix the RFID reader on a robot, and once the robot passes through the particular area, automatically it will read the number, the unique number in the respective RFID tag. So when it gets that data based on programming, you can identify that it is in this particular location, because we have already set in our hardware that in our hardware programming that we have, if this particular number unique ID means this particular location. So based on that location, the robot can decide which direction to move next and which node to go. So then it will move to another node, and then it will encounter another RFID tag, and so you can confirm that it has reached the next location, and then you can move on to the next location. So like using this, we can implement an autonomous navigation system based on this shortest path finding robot based on Digistra with the RFID tags. Then sensors and actuator interfaces like dynamic cell, fidgets, Arduino, Robotics, Lego NXC. So these are all different kind of robotics development platforms which we can use for developing robots, ROS robots. Then simulators, we can also do this using hardware, and also we can implement this using simulations. So simulator stage. Stage is a 2D simulator. It's a 2D simulator. So to learn the whole system programming and all that, we don't need to buy the whole hardware and work on it. You can just use a simulator to start with, and then you can use hardware to implement different things. And multiple large-scale mobile robots and models for sensors. So there is also available in stage. There is different sensor models are available, like laser sonar and actuators like grippers and other kind of motors and things like that. Then models of simple objects for limited manipulation. Then no objects, no physics model at all, like friction, collision, and so forth. And then simulator gazebo. So this is a 3D simulator. So this is a 3D simulator. It's called gazebo. So we can use the gazebo simulator to make a robotic application or ROS applications. Okay. Then so robot can be classified into two different type of robots: manipulator or mobile robot. And in manipulator means they're just the same as the robotic systems that we saw before, like the same robotic systems that we saw before, the Unimate and the Unimate is another example of a manipulator. Manipulator means a fixed robot, and these are like the different features of a manipulator robot. Like robots just stand in its place and still moving to do work with its arm. These robots known as automatic control and doing same work repeatedly. For example, school installations. These robots are suitable to do work that is boring and tedious for humans. Then can be programmed or to do other tasks. Then examples are like forging robots, assembly robots, blocking for car parking, robotic arm. Then mobile robots. Mobile robots are like robots or wheeled robots, and these are like different parts of it, features of a robotic mobile robot. Can be a rail or a track, or can work with the several places, can move to walk by itself, and movement using wheels or foot or rail. The tasks that are being done by robot needs to make it move from one place to another place. Then workspace may be dangerous, difficult, or wide. So based on the type of scenario, and then type of dynamic robots. Then manipulator, robotic components manipulators, the main body of the robot. Then end effector, the part that is connected to the last joint of a manipulator. Then actuator, different kind of stepper motors, actuators, and then sensors, different kind of sensors to collect different data. Then controllers, processors, software. We already discussed all these things. So we can different. Okay, then end effectors in robotics and end effector. It's a device that arm or something like that can be an end effector. Locomotion actuators can be of different type. Locomotion manipulators, these are all these things. Then controller. So first, basically, we have to start with the controller. So we don't have the time to go into details of the controller Arduino. So we can use any kind of platforms, controller platforms, Arduino or PIC or any kind of basic controller platform to implement the robot. Or we can use any kind of single board computers, because single board computers have embedded computers have both GPIO connectivity and also normal OS based processing capabilities. So they can be used in say the single board computer can be used for making a complete robotic application with the computer vision and all that. So then here, so the basic part when we discuss the ROS robot, SLAM robot, the basic part of the robot is a microcontroller which can control DC motors or any kind of actuators. So this is an example of a microcontroller or a microcontroller board. So this is Arduino Uno. This is one of the most basic Arduino platform boards. So we can use Arduino Uno to program and make different kind of applications, robotic applications. So we can basically it can be used in robotics. It can be used for controlling simple actuators like DC motors, servo motors, stepper motors, and for interfacing simple sensors like proximity sensors, like ultrasonic IR sensors, or lidar, single time of flight TFT lidar. Then Arduino. So Arduino is most preferable in case of developmental case, because we can easily make an application using Arduino, because we don't need to go into theoretical like in depth. You don't need to study in depth about the hardware architecture of the microcontroller to start with Arduino. So that is one advantage of using Arduino, and you can use so Arduino can be any of these three things: a physical piece of hardware like Arduino Uno, or a programming environment which is open source. Programming environment, Arduino IDE is an open source software, and also community of philosophy. So like ROS, there is an online community which we can use for developing different applications. If you have any queries or any doubts or anything, you can easily find the answers through these support systems. And easily we can get started with Arduino by just downloading. So I think our time is finished. So I have to wind up now. So we have gone through some like we have started from the like the history, and then we have gone through some like the 20 some earlier developments in modern robotics, and then what is happening in robotics, basic robotics in now. So robotic operating system, we saw what is robotics operating system. And then the first step in any robotic or in any robotic application is to make the basic robot setup. So we have to use some kind of development platform to do that, microcontroller embedded development platform to do that. So here we can use here in this case we can use Arduino IDE to develop the application. So we can just easily start it. So everything is open source with Arduino, so we can just easily start with the Arduino, and we can continue from there. So after making that, you can get familiarized with a single board computer like a Raspberry Pi or a Jetson Nano, or any kind of Jetson variation, or a Edison board, any kind of board like single board computers. Then you can try to implement the other part. So we can, so the any kind of robot, any kind of a high level or low level, whatever it is, the initial step is to study how to program and interface different kind of actuators using a basic developmental program. So thank you. Thank you all for participating and listening to me. So I just hand over to the staff. So to wind up.
Thank you, sir. Thank you for
Yeah.
the wonderful presentation. I
Yeah.
hope
Yes.
it is really helpful for all the participants who are
Thank
viewing it from YouTube.
Thanks. Thank you.
So hope in future also we may conduct such kind of events so that participants can get more insights in all those topics. Thank you, sir. Thank you for your wonderful presentation. So, as a token of vote of thanks, I formally thank all the faculties and staffs behind for conducting this webinar. I especially thank Ramco Institute of Technology and Pantech eLearning for collaborating and conducting this wonderful webinar. So that's all for today. Thank you everyone. Thank you.